All right.
So what we'll do is, starting this class, we'll start discussing orbital maneuvers. So the first kind of orbital maneuvers we'll discuss is impulsive maneuvers. So what are impulsive maneuvers? Impulsive maneuvers are a definition is refiring of on-board rockets or thrusters which result in the change of magnitude and direction of velocity vector instantaneously. Okay. The basis of this what is the basis of achieving orbit maneuvers or change in magnitude and direction of velocity vector instantaneously? Unlike, so here, recall Newton's second law. So what does Newton's second law say? It says force is it says a change in momentum will, if you apply a force, the force will result in a change in momentum. Okay? Now if you take the derivative of this, have if you take a complete derivative of this, you're going to get m v dot plus u dot e. Right? Typically what we do is for ground vehicles, ignore m dot. We ignore change in mass, but that is not the case for rockets or for satellites. That is solely how you can impact a velocity change. Okay. How do you impact a velocity change? How do you impact numbers? You can play games later. It's not that important.
So was that a rhetorical question?
So typically we ignore this, but this is the reason you see a change in magnitude and velocity vector in impulsive maneuvers. Okay, so what is this m dot?
Mass flow.
M dot is delta m or change in mass in the context of satellites and rockets. This is
Like
change in
view.
thrusting, let's say, fluid or even sometimes solid. In a solid booster, the rockets will be mostly solid fluid. Okay, this causes thrust. This causes impulsive maneuvers. Okay. If you look at this equation, will give you magnitude delta V of the velocity increment. Related to delta mass of current. So this term delta V is very important actually. It's what is this delta V? Delta V here.
Change velocity.
Delta V just means change in velocity. Change in velocity. And delta M is change in the mass of propellant. You understand propellant, right? Most of you understand propellant?
Yes.
All of you? Does anybody not understand propellant?
Propellant.
Propellant is what? Something which propels. Okay. So you have you seen a typical? Have you flown any? Have you participated in any rocket competition? Or any? All of you?
We did some rocket launch propulsion class.
Right. So this is called the ideal rocket equation. Okay. So here delta M is change in mass, M is the total mass. You can say it is rocket or orbiting body. What is the difference between rocket and orbiting body? Can an orbiting body be a rocket? Yes.
I was say rocket has its own propulsion. Well,
Orbiting body doesn't have its own propulsion.
it can because satellite propulsion. Rocket.
Can a rocket be an orbiting body? Okay. So what is so special about a satellite?
It has its own rocket propellant and it orbits.
When the rocket is used, like press, push it around and over it, and only the body is used gravity.
A rocket is not in any particular orbit because it's moving on its own.
What is the purpose of a rocket? The purpose of a rocket is to send something useful into an orbit. That's it. It's not active after that. Although it may be orbiting, it will go into a. There is a lot of junk in our orbit, right? There is a lot of debris in our orbit. So rocket bodies are one of the biggest orbital debris out there. So once the rocket goes up there, it's dead. It doesn't do anything, although it's orbital. A satellite would have something more use. It would have some kind of payload. It will do some kind of utility once it goes up there. But satellites will also have small rockets. Will have small thrusters. Okay, it will have this propellant. It will have exhaustible or consumable propellant, or it could be electric propellant, which can be recharged. Okay, so this propellant will be there in a rocket, and there will be small thrusters in your satellite. Okay. Principle is the same, whether you talk about rockets or you talk about satellites. Principle is the same. This equation causes. This is how you evaluate what is the delta V. Okay. What is the delta V? How do you relate? Here, everything is a constant. Right? You see that? Only this is changing and this is changing. Delta V is very specifically a function of this delta M. What is ISP? Is the specific impulse. So it's essentially you understand what specific impulse is? Impulse per unit mass. So it's essentially the calorific value or how much impulse the propellant. It's a property of the propellant. Each propellant has different properties, right? So the same amount of propellant, if you take two same amounts of propellants, one can produce more thrust than the other, just because of its material properties. So this is that specific impulse property. Okay. G naught is sea level standard. This acceleration doesn't change. Yes.
You said delta V is a function of delta L.
Right. So everything else is a constant. This m is a constant, right? This is what is this m?
Total mass.
Mass before it. After every impulse. Before the impulse, what is the mass? Okay. This delta m is the change in mass. This is a constant, right? Before it goes up there, this will be a constant. So this delta V is simply a function of this delta M. It's purely a function of this delta M. How much mass is lost, and you can relate that to this. So what that delta M causes, what does this delta M cause? What does this do? You see this m dot is negative, right? Is this m dot negative?
Yes.
Why is it negative?
Because it loses mass as
It
time
loses
goes.
mass, right? So if it loses mass, this becomes negative. So what this causes is, this mass loss causes a change in force, right? What is force? Do you understand what basically force is? What is force?
Applied to a direction.
Huh? So change in momentum causes force, but what is force itself?
Mass times acceleration.
Huh?
Mass times acceleration.
Mass times acceleration is force. This is mass times acceleration. So don't pay attention here. We cannot apply mass times acceleration to this when we study rockets or when we study satellites with thrusters. So this is that mass times acceleration. This component you see here is that mass times acceleration. But the complete Newton's second law is this. Change in momentum. You know how to, see, you know what mass is. You know how you can impact velocity. But can you tell me what forces, basically fundamentally what forces? Do you understand fundamentally what forces? We don't understand fundamentally what forces.
We don't. So that's a trick question.
That's a trick question. So that's what you should know, right? So what is force? What is gravitation? Do you fundamentally understand what gravitational force is? You accept that there is fundamental gravitational force, right?
What goes up must come down.
Not necessarily. The rockets don't come down. Satellites don't come down, right?
Well,
All right. Let's keep the discussion the same. But fundamentally, we don't understand force. That is something we accept. Do you understand what's electromagnetic force?
yes.
Huh? Do you understand what gravitational force is?
I mean, we know what it is.
We don't understand, we accept. Do you know what weak nuclear, strong nuclear force is? Do you know why they bind together?
Yes.
Hmm?
No, I think we don't really know.
We don't really know force, okay? But we know how to.
Do you mean like you cannot see that?
We don't know. See, that is the binding. That is what we are trying to understand. So we understand, we accept that there are four basic types of forces in nature. Gravitational force, electromagnetic force, weak nuclear force and strong nuclear force. But we don't know what that force is. What is that force? What causes that force? What is fundamentally that force? Can you define that force?
Essentially, what you're saying is we can't associate mass with force.
Hmm?
We can't associate mass.
We cannot associate. We can say, what is torque? Torque is another kind of force. But we know how to apply torque. But do you understand torque itself? We don't understand. Do you understand inertia itself? Do you understand inertia? Huh?
You just accept it.
You accept inertia. You accept that there is inertia. Inertia will change if you apply force, right? That's what Newton's first law says. A body, how do you define? Newton's first law defines inertia. A body continues to stay in rest or in uniform motion unless acted upon by an external force. So what that defines is inertia. But do you know what inertia itself is? Can you define inertia itself?
How do you differentiate between what you accept and understand? So, can you give an example of what?
That's what I told you, right? You know, if you look at this, which part do you understand? You understand mass. Mass is what? You understand it very fundamentally, right? You know atomic number, you can associate atomic mass, then you can associate how many molecules.
Or whatever quantity you can go further, subdivide, then that means like understanding.
Right. So velocity also you understand. Change in position is velocity. Right. But do you understand force itself? So what you know is, if you change, this is how you define momentum, right? Mass into velocity. This is what you accept as momentum. Now, if you change this, that will cause a force. That is what you know. But the force itself, you don't know what. Can you strictly say, do you experience force in this room? There is always force, but you don't necessarily understand. Yes.
For this equation, is that last term, is it raised to the e or is it subtracted?
It's raised to the e. Raise e to the power of minus delta v over ISP.
Okay, and you said that was the general orbital equation? What is it?
This is the ideal rocket equation.
Ideal orbital equation.
Okay. So this you'll get from the exam point of view, from an assignment point of view, you may be given as a spacecraft engineer, what you are required to do as a purely satellite engineer. You're required to figure out this delta V. What is the delta V required to go from one orbit to another? This orbital maneuver, what is the purpose of orbital maneuver? To go from one orbit to another. Okay? So how do you go from one orbit to the other? Is there a need to go from one orbit to the other?
Yes.
There's always a need, right? So if for example, if you want to go to the moon, you cannot just go there, right? What are you going to do? You're going to go into a circular orbit. You're going to park there for a while, then you're going to orbit there for a while, and then fire your thrusters, and then go on up. You're going to spiral and then go towards the moon. So you're going to change your orbit. You're going to keep changing your orbit.
So, in both experiments, what you use to orient body in a certain direction, right?
You can use them for that as well, but here we're talking about change in translational motion. Orbital maneuver is change in translational motion. What you're talking about is change in rotational or orientation. So you can align it as well, but you can use something like electromagnets, or you can use something like gyroscopes to realign yourself.
So I was going to ask, if you use an impulse rocket to line yourself, don't you have to use an opposite impulse rocket to stop yourself?
Yes. So what you do is, see if I'll talk about that here. So let's talk about what a maneuver is. Okay? Let's say this is your orbit. So let's say your orbiting body is here. Okay. Now what is the position vector of this? This is the position vector, right? This is r. And what is the velocity vector? Velocity vector is perpendicular, okay? This is your v0. Right? Now if you want to go into, let's say, this orbit, right? So this is your target orbit. We'll say this is the initial orbit. This is the target or final orbit. So what you're going to do is,
You need escape velocity. Do you need an escape velocity? Like that, or-
so this escape velocity is not. We don't have to go to escape velocity right now. We're still going to be in this orbit only. We're still going to be under the gravitational this thing of let's say Earth. And we are not so keen on going somewhere. We're just keen on changing our orbit, being in the vicinity of Earth. So what you do is, so let's say this is my thruster, okay? This is the direction of my thruster, right? Now, this is how it is, let's say, orbiting. Or let's say this is how it's orbiting. When you come here, if you want to go into this, you figure out the change in velocity. You need to understand here, this is V0, and this could be your this is V0, okay? And this is V1. Right? This is V1. From here to,
From where to where is V1?
again from this point to this point.
So where's V0?
V0 is this point to this point. The length indicates the magnitude of the velocity. This velocity, V0, will keep you in this orbit. V1 will take you into this orbit.
And then once you get in that orbit, you'll stay in the next orbit.
You'll stay in the next orbit.
So the difference between
This difference is delta V.
Yeah.
The extra, this extra, is delta V.
So if you were to look at them as two rings,
Huh?
delta V would be the space between the two rings. Like if you look at V0 as this ring, and you look at V1 as this ring,
Right.
the distance between the two would be delta V.
Delta V would be here. You can compute based on the position, you know the velocity. Based on what orbit you want to go, you can figure out what this V1 is. What is the required V1 to go into that orbit? Then you're going to when you do that, when you figure out, see, you know the direction of this delta V as well. The direction has to be perpendicular. So if it has to be perpendicular, I have to align my satellite perpendicular first. I cannot fire in any direction. What happens if I fire like in this? It will go into a smaller orbit. If I fire it in this, right? It always follows Kepler's third law. Right? If you change, if this distance changes, right? The orbit period is proportional to the semi-major axis, right? Or the distance. So if you change the distance, if you limit this, it will go into a smaller orbit. If you fire your thrusters, if you keep your thrusters in this direction and fire it, it will go into a smaller orbit. If you fire your thrusters in this direction and fire them, this thrust will create a force upwards, and then it will go into a larger orbit. So that is the delta V. As orbital engineers or as spacecraft engineers, as satellite engineers, you are required to find this delta V. Largely your goal is to find this delta V. You'll be given, let's say, an orbit. I want to go from this orbit to this orbit. You have to find this delta V. Yes, Thomas.
Would you keep repeating this process considering the orbits you want to be in?
Yes. So what you can do is you don't have to fire. If you want to be more precise, if you want to be more accurate, so you keep on increasing it by little. So impulsive maneuvers is unlike your vehicles or unlike your aircrafts, you don't constantly thrust for rockets and for satellites. You understand why this is impulsive maneuvers? You just fire the thrusters once for a certain period of time, let's say a minute or a couple of minutes. It will change the orbit and it will keep in that orbit. Okay? So what in aircraft you don't do that, right? You have to continuously keep firing thrusters or using propellant to keep in a particular this thing. Even for cars, ground vehicles you have to do the same thing. Okay? It's not so for satellites. If you fire your impulse, if you have one impulse here, it will go in this orbit and it will keep in that one. Again, what happens if you come back here and then fire the thrusters again? It will go into a larger orbit, it can go into a smaller orbit. Okay? Alright, let's discuss something called Hohmann transfer. By definition, see this Hohmann transfer was actually discovered or proved by Hohmann in 1925. Okay. So what it is, it has very high significance. All your moon missions have been possible because of Hohmann transfer. So Hohmann transfer by definition is the most fuel efficient through impulse maneuver for transferring between two coplanar circular orbits So there are lot of things to remember here. One, it starts with the most fuel efficient. Okay? Is fuel efficiency important? Will you go up in space? It's by far the most important thing for space mission. More fuel, more mass, more money. Okay? 2 impulse maneuvers. So we'll get to that. Transferring between 2 coplanar circular orbits, sharing a common focus. What does that mean? Sharing a common focus means,
One is smaller than the
huh?
other. One orbit is smaller than the other.
Sharing a common focus means,
They have a intersection. They intersect at some point. Their orbit.
Yeah, same center.
Same center.
it's orbiting around the same body. So we are really not talking about going from Earth to Moon.
Okay.
So Earth to Moon, does Earth to Moon, if something is going from Earth to Moon, is it sharing the same focus? It's not sharing the same focus, right? Because what's going to happen if, of course, it depends how you look at it. Because if something is orbiting around Moon and coming back into Earth, you may think about that as sharing the common focus. But we're talking about, so this is your, let's say, Earth. This is the first circular orbit. And this is the So what you're seeing here is you have, so now look at this definition. Most fuel efficient 2 impulse maneuver for transferring between 2 coplanar circular orbits. These are in the same plane. That is also very important because in-plane transfers and out-of-plane transfers are very, very different. Are very, very, as much as possible, you want to keep your transfers in plane. Okay? So this is the same plane, they are in the same plane, right? So initially, this is the, let's say this is the initial orbit. And this is the target orbit. So what you're going to do is, you're going to get into this initial orbit, okay? At this point, this is the transfer orbit. Can you go from this orbit to this orbit directly? Can you go from this orbit, the initial orbit, to the target orbit directly?
For example,
You look at the target orbit.
Are you talking about is it efficient to do this?
Huh?
Are you saying is it efficient to
Can
do
you
it?
do that?
Not do it.
You
You
could.
can't
I
do
see,
it.
I see why you need the transfer.
You
can't just hop into the next
You
orbit.
cannot just hop into another orbit.
Okay.
You need a common point for any transfer. Okay? So what you're seeing here is, so this is the periapsis, right? Let's say the periapsis for and let's say this is the apoapsis. So when I'm talking about periapsis and apoapsis, which orbit I'm talking about? Transfer orbit. Right. Okay. Now, let's say this distance is R1 and this distance is R2. Okay. So the first orbit and second orbit, if you know R1, R2, you know it just means since it's a circular orbit, this R1 will remain the same for first orbit. This R2 also will remain the same for the target orbit. What is this R1? This R1 is also the RP for the transfer orbit, right? And R2, so here I'll write R1 is RP, okay, and R2 is what? RA. Correct?
I'm not understanding the transfer.
So the transfer orbit, I'll tell you the transfer orbit. So what you do is, this is the, let's say the initial orbit, you just use a rocket to go to the initial orbit, right? The rocket goes up to the initial orbit and it will just push you into that. It will just launch you into that. Now, how do your final orbit is, your target orbit is this, right? Why don't want to go from this to this using a rocket?
Oh, I see what you're saying now. You're saying why go to a straight? Oh.
No. Why won't you go from this? This is your Earth, right? If this is your target orbit, why would you not go from here to here directly?
Because that's because you want to use all your fuel fighting gravity trying to go that way when you just.
Anytime there is a rocket, right? There is an extra mass you need to carry. 70-80% of the rocket is what? Fuel, right? You don't want to carry any extra weight beyond what is required. Once you get into the circular orbit, once you get into an orbit, you need very little energy to go to another orbit. Why do we need such big rockets?
To overcome the Earth's gravitational pull.
That is one thing, but why don't we need such big rockets when we are here, when we are in an orbit?
Because of inertia.
I mean, it's like
The reason we need rockets is because there is a lot of atmospheric drag. It's not so much about gravity. The gravitational force will not decrease a whole lot when you are in a lower orbit, right? But the atmospheric drag will decrease significantly. To overcome that atmospheric drag, there is a lot of atmosphere, right? To overcome that atmospheric resistance, you need rockets. You need huge rockets. But once you're in an orbit, you don't need a whole lot of fuel. You don't to overcome. All you need is simple maneuvers. You have seen gravity, right? A simple thrust can push you just away. And if you see moon, why can you bounce on moon? Or if you see some of the cartoons, if you just push somebody on moon, that person may just go. Because there is no atmosphere on moon, right?
So our transfer orbit is not a circular orbit.
Transfer orbit is not a circular orbit. Transfer orbit itself is an elliptical orbit.
Oh, that's supposed to be.
Yeah. But why does it go back around? Why doesn't it just go out there and stay out there?
Huh?
Why doesn't when you're going
that's what I'll tell you. So what you do here is, you get to this point, okay? So here, so this is V1, okay? V1, and this is, let's say, VP. Is V1 and VP the same?
No.
V1 and VP is not the same. Although R1 and RP are the same, V1 and VP cannot be the same. You got it? So V1, VP minus V1 is delta V1. You get to this point, you increase the velocity by delta V1. You'll go from the circular orbit to the transfer orbit. Okay, you'll keep orbiting in this transfer orbit. You'll get into the elliptical orbit. Now, here, this is, let's say, VA, right? And you need, this is V2.
And V2 is the target.
And V2 minus VA is delta V2. So you come to this point, and what you do is, you increase the velocity by delta V2. Then you go into the circular orbit.
Okay.
So you see why it is two impulse makes sense. You have one impulse which will take it into the transfer orbit. The second impulse will take you into the target orbit. So now I'll also prove why it is the most fuel efficient this thing. But try to understand this. You understand? For now, just don't worry about this. Two impulse, you understand? For transfer between two coplanar circular orbit, you understand? Sharing common focus, you understand? See, every orbit, all these three orbits have the same focus, or the same central body is the same.
So the center is the same. The focus is the same, or the center is
The focus is that the central body is at the focus.
So this is a circle. These are all circles.
So essentially,
No, this is circular, but don't make that mistake. Central body is always at the focus.
Yeah.
It is not at the center. Even for an ellipse, it is at the focus. It is not at the center.
No, the center. Okay, so where's the center on this?
So the center for these two is the same. What is the center for transfer orbits? Center and focus for circular orbits is the same.
Yeah.
But center and focus for elliptical orbits is not the same. Okay? But the focus is the same for all three orbits.
I see what you're saying. It's just doing the transfer.
The central body is where the focus is. Or the central body is at the focus. So it is the common focus. Okay, so you understand this? This is pretty simple.
Yeah,
Right.
can you go ahead and do the two impulse things again? You said what was one impulse and what was the
So you-
second impulse?
What you're going to do, you're going to take a rocket. Okay? And then you're going to get into the circular orbit. Then you're going to ditch your rocket. You're orbiting, you come to this point, you come to the periapsis. Or you come to some point and you fire your thrusters. You align your thrusters in the velocity direction. Right? And then you want to fire your thrusters. That is the first impulse. Once you fire your thrusters, and the velocity is needed is delta V1. Got it? You're going to go into the transfer orbit. You following me? You'll go into the transfer orbit. Transfer orbit is also called Hohmann transfer elliptical orbit. The transfer orbit itself is an elliptical orbit. You're going to keep going here. Once you come to the apoapsis of the transfer orbit, you're going to align your thrusters. Thrusters are going to be pointed this way. You're going to fire your thruster in this direction. So you can create velocity in this direction. Right? Once you create that velocity, once you change that velocity, it will go into the bigger circular orbit. So one impulse, two impulse. So that's a two impulse.
So for that over that schematic over here,
Mm.
Because it started off in an elliptical orbit, it was able to go straight to the target, or should that actually be a transfer of the orbit?
See, it depends on what orbit your target orbit is. Okay. Your target orbit in most cases is not. You're not so focused on the orbit itself. What you're focused on is covering a certain area. Okay. Now, if this is your Earth, okay. If my mission requires to cover a particular part, let's say once a day, twice or once in 2 days, I may be able to do that being in this orbit, right? So what I'll do is I'll just change. I'll do one maneuver. I'm happy with that, as it's covering my mission. Now let's say I want to launch a GPS satellite. GPS satellite has to be this orbit, right? Something like this. Any GPS satellite has to be in a circular orbit, and it has to be really, really far. Correct? You're not going to take your rockets up to the GPS orbit. So what you're going to do? GPS orbit has to be an equatorial circular orbit. You're going to go into a smaller orbit, ditch your load, okay? Then you're going to do one or more Hohmann transfers.
Okay. Which
Right.
Each one of those includes two.
Each Hohmann transfer will include 2 impulses. So you need not go to this orbit in just one Hohmann transfer. You can do this. In between, let's say, if this is your initial orbit, you can go into this orbit, then you can go into this orbit, then you can go into this orbit, right? So what you do is, this is your first Hohmann transfer, this is your second Hohmann transfer, this is your third Hohmann transfer. So you'll keep on doing one transfer after the other, right? That's what you want to do. Got it? So every Hohmann transfer will require how many impulses? 2 impulses. And every Hohmann transfer orbit is an elliptical orbit. Alright, I think we can stop here. Let's discuss a little bit about this thing. Your exam will be on Thursday.
Next Thursday, right?
Not this Thursday, but next week Thursday. Okay, and you'll get one more assignment. The next assignment will focus on coordinate transformation. Okay, try to use MATLAB again. Try to use. I've seen most of you using MATLAB for doing arithmetic. There is something called symbolic math toolbox. You've heard about it? Symbolic math toolbox. So if you want to do algebra, you might be able to do algebra using symbolic math toolbox. I told you computers cannot really do algebra. They can do arithmetic. Mostly they can do arithmetic. But you can emulate some of the algebra. You can define how the way we are taught algebra. This into this is equal to this. Then if you do the same thing in computers, they'll be able to do that. Right? So you can use symbolic math toolbox to do some of that algebra. Now I'm going to give you an assignment which is really focused on coordinate transformation. You have to understand that coordinate transformation. It's very important. See, for example, here, why is coordinate transformation important? You understand why coordinate transformation here is important? Huh? Huh? The inertial frame itself will not change. See, what you need to know is, once you're out in space, will you know what your orientation is just by looking around? So you have to precisely determine your orientation relative to See, you'll be in so much this thing. So there'll be, if everything is space around, right? When you want to align your, you have in space, you don't have more than one or two chances. You lose that one or two chances, what happens? You may never come back.
Oblivion.
That's actually true. You may never come back. If you lose that one or two chances, you'll just stay there. So when you take those one or two chances, you have to be very precise. Now you have to align. If you align, instead of aligning it like this, you align it just a little bit off, you'll be somewhere else. So how do you align it like this? How do you make sure you're aligned like this?
Yeah, like something like reference.
Huh?
Yeah.
You have to reference. So this is orientation. This alignment is a orientation, and coordinate transformation is very, very important. So this alignment is a function of your body frame, right? You have to know your body frame, and then you have to figure out what that body frame is with respect to the inertial frame. Only then you're going to get the right impulse, or the impulse in the right direction. Otherwise, if you may go into a smaller orbit. You understand?
Can you put the solution to 4.2 on that?
Huh?
Can you put the solution to 4.2 on that?
4.2.
Yeah, wrong 4.2. Why not?
I can explain to you the solution.
I don't know how to find
Huh?
E by itself.
You don't know how to find E?
That's not
I don't know how to do it.
We all have problems.
I'll show you how to. We'll discuss 4.2 in one class.
Alright, you said something.